This lecture will cover quality assurance in ultrasound. So what is quality assurance? Well, we define it as routine, periodic evaluation of an ultrasound system to guarantee optimal image quality. We need it to validate consistency of images and the accuracy of the ultrasound system. When we consider quality assurance, we need to make a quality assurance action plan. Typically, this is going to be arranged either by sonographers or if you work in a larger hospital through your biomed department. They are the ones that typically take care of machines, the IV poles, the CT, all of that. That is not covered by the manufacturer anymore. Your action plan must be enacted periodically and routinely on each component of the ultrasound system. So not only are we checking the actual machine, but we need to check the probes, we need to check the cleaning devices, we need to check everything that goes into our studies. And this is going to be a medical and legal necessity for every laboratory. So if you have an ultrasound machine out there, it needs to be tested for quality assurance. So the requirements of a quality assurance program are to, 1, assess the system components. So when QA is performed on a machine, you're going to be testing all the knobs and buttons, make sure that they do what they're supposed to do. We're also going to take a look at the probes, make sure that they are also doing what they are supposed to do, that there aren't any broken crystals. After the assessment of the system components, if needed, then repairs should be done at that time. So oftentimes, maybe the TGC knobs get out of whack, maybe the mouse ball doesn't work very well. If that isn't working well, then we need to make repairs. During the quality assurance assessment, it'll also be a good time to do preventative maintenance on our machines. So that'll mean cleaning them. There are filters that bring air into the machine, and the filters will catch out the dust and kind of junky stuff that's out in the air so it doesn't clog up the machine. Well, we need to vacuum those filters so the machine doesn't overheat and can work appropriately. Another thing that we can do through preventative maintenance is to run a diagnostic on the computer component of the ultrasound machine, and as computers run into errors during their operation, they'll kind of create a log of this, and running a diagnostic on that can bring up those errors that maybe somebody didn't catch or somebody wasn't aware of. So then we can kind of look into it, is this going to affect how the machine is working? And the last requirement of a quality assurance program is that we keep records of it all. We want detailed records, the date it was performed, when it was performed, who did it, and what the findings of it were. So assessment of system components, repairs, preventative maintenance, and record keeping are the 4 requirements of a quality assurance program. You're going to want to know those. When we are performing quality assurance, we want to make sure that we are testing under known defined conditions, that we're going to use constant instrument settings, and to do so, we'll typically use a phantom with measurable characteristics, and we're going to make sure that we're imaging in identical environments. So typically, when a quality assurance program is set up, you're going to do quarterly QAs, and so maybe you'll do it every January, every March, every August, and every November to make sure that you're doing it at the same time in identical environments. Humidity and temperature of rooms can affect how the machines work, so we want to make sure that we are trying to recreate the same settings as we do these quality assurance methods. We're also going to use the same settings on the machine. We're going to keep our mechanical and thermal index at the same level. We'll keep the power at the same level, the gain output at the same level. Everything should be identical when we do our quality assurance. We want to keep everything identical because it'll help us to identify objective versus subjective standards. Objective standards are factual, measurable, repeatable, and not opinion-based. So if we are keeping all of our settings the same, then it's not, well, I think it looks a little different. Nope, we should be able to tell, measure it, that it is definitely different. Subjective standards are going to be more influenced by belief or experience, and they're also going to be based on perceived reality, and it's going to vary from person to person. So with ultrasound, you might have people that like to image at different brightnesses. So we talk about, well, I'm kind of a dark imager versus a bright person. Those are going to be subjective standards, like, well, I think the machine is doing fine because I like dark, where somebody else might say, hey, I think the machine's broken, it's imaging really dark. Those are subjective because it's going to vary from person to person. If we have a good quality assurance program and we are finding that the machine is not imaging at the correct dynamic range, then yes, we can measure the fact that it is definitely imaging darker than we would expect it to. And that's going to be an objective standard. So recognize the difference between these two. So when we talk about wanting to have the same settings when we are doing our quality assurance program, we are typically going to use some phantoms or other devices to help us maintain the same settings from each quality assurance check-in. So we use beam profilers, tissue equivalent phantoms, and Doppler phantoms to test the machine. So the first device that we may use is called the beam profiler, and this is also known as a slice thickness phantom. The purpose of the beam profiler is to determine the beam width and then also determine the elevational resolution. The beam profiler phantom is made of kind of a jelly material that is going to be the same as a soft tissue medium. And then there's this really thin layer of echogenic material, which is actually graphite. And it runs at a 45-degree angle through the beam profiler. This is going to help us to be able to measure the beam's width and check on that elevational resolution. So when we put the ultrasound transducer on that angled part right here, there is that scattered areas running at a 45-degree angle through the beam profiler. So if we put the transducer right in the plane of that scattering line, we're going to see the beam's profile. We can see in our image here, this is actually an ultrasound beam showing us the width. This first picture is with a single focus, and we can see it's thinnest right here, lines up with where that focal point is. The next picture shows a multifocal ultrasound beam. We can see that there are five ultrasound focal points going down the side here, and we can see how the beam stays relatively thin throughout. And then here we have decreased our transducer probe. We've left the multifocus on, and we can see how these are a little bit wider as they go out, just with the decrease of the frequency. So this is actually going to show us a very nice picture of what our beam looks like. So then to test the elevational resolution of our ultrasound beam, we're going to switch up to the top part of our beam profiler. And as we do that, we're going to be hitting that scatter line a little bit differently. And when we do so, our picture is going to show us more of a horizontal bar going across. And to understand how thick the beam is, we are going to measure the vertical portion of that bar, and that'll tell us how thick our beam is. So when we're down on this side here, we got our width. This will tell us our thickness. Another device that we're going to use to test our machines are tissue equivalent phantoms. The purpose of these are to have something that we can consistently evaluate our ultrasound system with. So with the tissue equivalent phantom, we can test things such as the grayscale, tissue texture, look at how multifocus affects our picture, and then how we can adjust and measure things within the body appropriately. The idea behind the tissue equivalent phantom is that it is made of a gel medium that's going to mimic soft tissue, and will keep the speed at 1540 meters per second. And within the tissue equivalent phantom, there are going to be strategically placed reflectors within the phantom. They're going to mimic cis and solid masses, and then they're also going to tell us where little pinpoints are to help us recognize, is the machine accurately displaying things as we suspect. And so that is where we can do our performance measures on. So here are some examples of our tissue equivalent phantoms. This top one is a pretty old one. and we can actually see those areas within the gel. We would expect those to look a certain way on the ultrasound machine. This one that this physicist is testing is probably a little bit more modern. You're going to have two interfaces that you can test the machine on, usually up top and on one of the sides. And you can kind of see it here, and we'll see one a little bit later. There's a map to what we should be able to see within that tissue phantom. And it'll tell us what decibels things should be displayed at, what measurements should be, how far apart things are, kind of a roadmap to what's going on in the phantom. This picture in the corner then shows us what the phantom looks like, and we can see that there's little bright dots in there. These are showing the dead zone of the machine. This is displaying the vertical accuracy, and this one is displaying the horizontal accuracy. So there's a bunch of things that we can test with these tissue equivalent phantoms, and these are going to allow us to keep consistent settings every time we do a QA. The last device that might be used during a QA is a Doppler phantom. So the purpose of this then is to assess Doppler modalities, and that'll include pulse wave, continuous, color, and power modes of our Doppler. There are a couple different types of Doppler phantoms. One is a vibrating string, the other is a moving belt, or a flow phantom, which is also known as a Doppler flow phantom. The construction of these are different depending on the type of phantom that we are using, but there's going to be a simulated vessel and then some sort of movement or pump that is going to be measurable and create the same pulsatility or waveform each time so we can measure it accurately. So this is an example of a vibrating string phantom. There is going to be a vessel that is static, so it's not moving, and then there's going to be strings going through there at different speeds that the ultrasound machine will be able to pick up because, again, Doppler picks up movement of things. So this vibrating string is going to create enough movement away or towards the transducer, and it'll be able to test the Doppler functions. Moving belt Doppler phantoms are going to work in a similar function in that there's just something moving within the vessels to record that Doppler function. And then the Doppler phantoms are actually going to have simulated vessels again with a fluid that moves through the simulated vessels by a pump that is able to be set so we know that we're getting consistent movement through our vessel, and then we can use our Doppler functions to test it. So we can test color and measuring the calipers on our spectral tracings. So this is an example of a Doppler phantom being used to test within a actual vessel with flow and color on it. So if you remember back a couple slides ago, we were talking about soft tissue phantoms being our kind of standard to keep all of our settings the same every time we do a QA program. So performance measures are something that we want to look at every time we do QA to make sure that our machine is operating appropriately. So the first performance measure that we're going to look at is the sensitivity of the machine. And when we do that, we want to look at normal and maximum sensitivity. Normal sensitivity is going to be where we have our machine set so that we can use it as we would normally on patients. And with that, we may see all the pins, we may not, but we want to see everything accurately. The opposite of that then is using the maximum settings, where we're going to really crank everything up to the top part of what we would use in practical levels. So granted, we keep our gain relatively low. The maximum, and that would be our normal sensitivity setting, where maximum we'd start to turn our gain up really high and see what everything looks like in the phantom. So again, we want to do a normal test, kind of what we would use in the clinical setting, and then we want to do a maximum test, crank everything up, and see what everything looks like in that phantom. Another thing we're going to test with our performance measures is the dead zone. And the dead zone is the region that is closest to the transducer where the image is going to be relatively inaccurate. When we increase our frequency, we're going to decrease the thickness of the dead zone. And this is always going to occur in the first few millimeters of any image that we look at, and they're almost always going to be inaccurate. So when we look at our sector and we see that really bright spot right at the top of our sector, it's because of all the interactions of the sound beams and what we call that dead zone. It's just not going to be accurate information up there. We recognize that we're not seeing the true skin and tissue as it comes in contact with the transducer. If we need to see very superficial on the skin, then we can use something called a standoff pad. And that standoff pad will help us to move the dead zone away from the actual skin line. So these are examples of what it looks like with a standoff pad and what those actually look like. So if you don't have a standoff pad available, you can just use a huge pile of gel and kind of float in your pile of gel. That'll help you to stay above the skin line and move that dead zone up. We also have ones that wrap around the transducer face or come in like little pillows of gel that you can lay on the tissue. But in the end, what they do is create this space in between the transducer face and the actual skin line. So now this is where all those inaccuracies are. This is where that dead zone is. We have the gel separating, and now we can see the true skin line and what's immediately below it. It's very nice for superficial bumps and lumps in the breast or really anywhere on the body. A couple more performance measures that we'll always be checking during our QA sessions are going to be looking at axial and lateral resolutions. So axial is going to assess reflections of pins that are placed closely together that are parallel to the sound beam, so ones that are going in this direction from our sound beam. And then our lateral resolution is going to assess the reflection of pins that are placed closely together that are perpendicular, so going across our sound beam. When you see them on the phantom maps, they're going to kind of look like little dots that go like this, and then they're going to curve up. So this portion will measure our lateral resolution, and this portion will measure our axial resolution. They typically place these groups of pins at different levels within the phantom, so we can test it in the near, mid, and far fields. Another performance measure that we'll be looking at is range accuracy. And with this, there's going to be pins that are set at vertical depths, and that will be able to tell us that on our map it'll say that measurement from the first one to the bottom one should be 10 centimeters. And if we're not getting that, then we need to calibrate our machine differently. Similarly, it'll give us little pins that are going horizontal, and it might say left to right is also 10 centimeters. If we're not measuring that on our phantom, then we'll need to reset the calibration on the machine. So this will make sure that we are imaging items at the appropriate depths and horizontal placements. Similar to this is registration accuracy, and again this is going to be accurate placement and size of the markers. So again, we're going to see these markers going down. We want to know that each of these are 2 centimeters apart. If at any point they are not 2 centimeters apart, then we're not registering the pins at the accurate level. And again, we would need to recalibrate our machine. Continuing with performance measures, we're going to check the compensation operation or uniformity. So we want to test the machine's ability to display identical reflectors at the same brightness. So on our tissue phantom, there will be a bunch of anechoic circles. We know that they should be anechoic, and we expect the machine to then display them anechoic. So if we have multiple anechoic structures and only some are anechoic, then we know that we need to readjust and account for that on the machine and recalibrate it. And then the last performance measure that we're going to be looking for are adjustments. We're going to change the power and we're going to change the dynamic range, and we are going to expect that the machine responds appropriately. So if I turn down my dynamic range, I expect that the machine will show me more black and white pictures. If I increase my power, I expect that the machine will appropriately brighten the picture. So we're going to check that all of our knobs do the correct things that they should. So here's an example of a map for a soft tissue phantom. These dots up here are testing the dead zone. These dots or circles across here are going to tell us how bright everything is, so this will test our adjustments that we're making. The vertical dots that are coming up this way are testing axial resolution. The ones that are coming across horizontally are testing lateral resolution. This set of dots here are testing horizontal distance or range accuracy. These dots along here are testing our vertical distance or range accuracy. And then these anechoic cylinders going up are also going to test the machine's continuity, that we're getting anechoic structures from near to the far field of our imaging. So you can kind of see how the map will tell us where things are and what to expect out of our tissue phantom. All right, so this lecture we learned about quality assurance. We know that either astronographers are going to be doing it or something will be set up through a biomed department, or a physicist might actually come out from the company that you buy your machine from, and they'll come out and test how the machine is doing. So you need to know what goes into a QA program, what we're doing with it, and what the goals of it are. You also will need to know the 3 devices that we use to test the machines, and you'll need to know the 8 performance measures and what they are and how we test them with a soft tissue phantom. So number 1, what are the requirements of a QA program? Number 2, what are the goals of a QA program? Number 3, what are the 3 devices used in a QA program? Number 4, how does the beam profiler work? Number 5, how does the tissue phantom work? Number 6, how does the Doppler phantom work? Number 7, what are the 8 performance measures and what do they tell us about the machine? And number 8, what questions do you have about this lecture?